professor of chemistry and a professor of material science and engineering at Stanford University. Bao founded the Stanford Wearable Electronics Initiative in 2016 and served as a faculty director prior to join the Stanford in 2004. She was a distinguished member of technical staff in Bell Labs, Lucent Technologies from 1995 to 2004. She received her PhD in chemistry from the University of Chicago in 1995. She has over 700 referred publications and over 100 US patents with a Google Scholar H index over 180. Bao is a member of National Academy of Engineering and the American Academy of Arts and Sciences and the National Academy of Inventors. She is a fellow of MRS, ISS, AAAS, SPIE, ISS, PMSE, and AS Polos. Bao was selected as Nature's 10 People in 2015 as a Master of Materials for her work on the artificial electronics. She was awarded the AS Chemistry of Materials Award 2022, MRS Mid-Career Awards in 2021, ASCHE Alpha Chi Sigma Award 2021, ACS Central Science Disruptor and Inventor Prize in 2020, Gibbons Medal by the Chicago Session of ACS in 2020, William Axner Medal by Australia Federal Minister of Science 2018, ACS Awards on Applied Polymer Science in 2017, L. Oriel UNESCO for Women in Science Awards in Physical Science 2017, ASCHE Andrews Agriworth Awards for the Professional Progress in the Chemical Engineering in 2014, ACS Carl Marvel Creative Polymer Chemistry Awards in 2013, ACS Koch Scholar Awards in 2011, Royal Society of Chemistry Bailey Medal and Prize in 2009, IUPAC Creative in Applied Polymer Science Prize in 2008. Today, Professor Zhenan Bao will give us a talk about the skin-inspired organic electronics. Let's welcome Professor Bao. I will stop my sharing. You can.
Okay, all right. And now it's moving into a new era that we call skin-inspired organic electronics or polymer electronics. So basically, transistor has been the key building block for all the modern electronics things. Its first invention in Bell Laboratories in the 1940s. It's a switch that's used to control the current flow within the semiconducting material. It's used for switching the pictures on the display and also for making integrated circuits. Today, most of the electronics are made with silicon as the key material, key semiconducting material, and silicon being rigid and brittle. As a result, the electronics we use today are also rigid and brittle. If we look at the electronics used for diagnosis and the monitoring, they again are very bulky and not so convenient to interface with human. Even for implantable devices, the current implantables still implant such bulky electronics inside the body, and this severely limits the possibility that modern electronics can offer for us to understand human health and treat disease. So what we envision is a future where electronics are comfortable, invisible, imperceptible, biocompatible, and even autonomous to be able to measure various different information and inform us about our health. And skin has been the inspiration for thinking about what are the characteristics to incorporate into electronic devices for decades. And starting from trying to incorporate sensors into prosthetic hand to more recently really to mimic all the different attributes of human skin, to think about new forms of electronics that we can develop. And important work in the field, pioneering work by Takao Sumiya's group showed that organic electronics can be combined with sensors, and that their organic electronics really has the advantage of being a large area, and but it only show the flexible electronic skin. And then the other really important work is John Rogers' work, where he showed that even with inorganic material, if you make them thin and then connect them with stretchable interconnects, then these type of rigid material can also conform to three-dimensional surfaces and potentially also make electronics stretchable. In my group, our work started from more than a decade ago, where we first wanted to learn how to mimic the sense of touch using flexible electronics. One important contribution we made to the field is to show or invent this microstructure that allows thin film flexible electronics to have the sense of touch that's comparable or even better than that of human skin. And that spurred a lot of activities in developing new type of sensors to mimic skin. But I think the important part that we realized while studying these sensors and how we make flexible sensors using polymer and organic materials was that we realized that skin is not only flexible, but also stretchable, biodegradable, and self-healable. And if we're able to incorporate these new properties into future electronic materials, then we can potentially completely change how the electronics interface with human. And furthermore, these kinds of new type of electronic material can allow us to truly learn how human skin sense and make electronics to mimic that and build the electronic skin that combines the sensing and the signal amplification or digitization, so that we can generate nerve-like signal that can be directly interfaced with biological system, because biological system basically communicate through electrical pulses to recognize shapes or recognize various external stimuli that it's exposed to. And in this case, our electronic skin should also combine all these functions that can reduce the computing power that's required, as well as being able to allow signal to transmit over long distance. So our electronic skin currently looks like this. This is our recent version of electronic skin, where we have integrated circuits that are fabricated onto this fully stretchable, intrinsically stretchable substrate, and with materials that are all developed from the beginning, and then including fabrication method. And now the transistors we can fabricate are at the density of similar to high resolution TV screen kind of density. So now these kinds of electronic skin is what we are hoping to further develop to really realize new possibilities for functionality. So in this talk, I'm going to talk about the materials development and then some applications of this. Before I go there, your question may be, silicon can already do so much with such a small chip. It can integrate all the sensors, many sensors, and also circuits and wireless communication all in such a small form factor. Why do we need the electronic skin? So what we are interested in is really to understand human health. And human health really is high level information that depend on the communication between electrical signal and the various chemical signal throughout the body. And all these signals are generated at the cell resolution, cellular resolution, which is not super high resolution in the tens of micron in size as compared to a few nanometers for the current state-of-art silicon technology. But these information have to communicate over centimeters to even meters distance. So in order to really understand how these information communicate with us, with each other globally, and be able to use that information to understand the human health or for future diagnosis, then we need a cellular resolution spread over large area. And for a silicon chip, it can be implanted in a particular region of the body and collect highly detailed information, but it will be localized in a specific location. While if we want large area, then we would need to have skin-like electronics to assist us. So basically what we are working towards is all the elements that's needed to build our future electronics that will allow us to either map the information on the body or even use this for human-machine interface in a new way. So all the elements include the circuits, sensors, displays, wireless system, and energy storage systems. And all of those, the key is materials development. So for the active material, there's of course the semiconductor, the conductors, and semiconductor really determines the speed of electronics, and they are the basic building blocks. And charge carrier mobility is what's important. Silicon, of course, is known to have high charge carrier mobility. Single crystal is the highest, followed by polysilicon and amorphous silicon. And similarly for organics, the pink shaded region is where organic electronic materials can achieve in terms of charge carrier mobility. A lot of work has been done by the field, by this organic electronics field over the past 20 years, including a lot of great work from groups in China and all over the world. And these single crystal, specifically single crystal organics molecules. I see Professor Hu's group is keep pushing this mobility to become higher and higher. But the important message is really that organics are already, in terms of electronic charge transfer, they are already start to be on par with that of even polysilicon. So the question is for us to try to think about how to build the next generation electronic skin is how we can really come up with a molecular design approaches where to have a good charge transport, the molecules need to be rigid and also have some crystallinity, but this results in brittle films that cannot tolerate much strain. But if we want a good mechanical property, then the polymer needs to be very flexible and but highly disordered, and then this result in poor electronic property. So how do we come up with design rules so that we can address this conflict requirement? From fundamental point of view, the way we approach it is to first understand what are the basic molecular level mechanisms that allows energy dissipation when a piece of polymer semiconductor is under strain. And through our study, we can conclude basically there are molecular rotation, chain elongation, chain alignment, crystal reorientation, crystal breakage, and bond breakage. Some of these mechanisms are reversible, but some are not. And the irreversible ones are the ones that cause cracks to form and also cannot return to the original morphology. So these are the mechanisms, the irreversible ones are the ones that we try to address and then lead to reversible morphology and the reversible electronic property. So one of the successful concept that we have reported a while ago was to basically think about how we can increase disorder, but at the same time not compromising the charge transport too much. There's always some compromising, but the key is to get both in the optimized condition. And to do that, we explored conjugation breaking mechanism to introduce some non-conjugated unit into the originally very rigid conjugated polymer, and that increase the disorder. And this can increase the crack onset strain from 20% to 110% after doing this, and modulus decreased by 10 times. And that is, we found still not sufficient, because if we use a simple linear LQ chain, the crack onset strain actually is still only around 50%. So to further improve that, we added hydrogen bonding site to add additional ways to introduce disorder and weak non-covalent bonding. And this resulted in a much more robust film. Even though there's a decrease in the overall mobility, but still the mobility of this resulting stretchable polymer can maintain mobility in the same order of magnitude as amorphous silicon, but with added stretchability. And next, we have been thinking about how we can really come up with a way to not sacrifice the charge carrier mobility. And staying with conjugated polymer is important. But these conjugated polymers, even at neat with the neat polymer, they normally form the morphology that's shown on the right by the AFM, essentially featureless. And there are some disorder, but you don't see any kind of distinct morphology, structure, formation. And we hypothesized that if we can have some kind of a network, nanostructure, then this nanostructure themselves could potentially allow a fishnet structure to allow better stretchability. But very importantly, we can't just mix some kind of nanostructure with an insulator and try to form a conductive, good conductive film because the nanostructures may not be well interconnected. So we have to figure out a way to induce nanostructures to preform already in solution. And we found found that adding these SEBS type of polymer can induce aggregation formation. From the UV vis, we can see the aggregation peak increase as we increase the amount of SEBS, indicating their pre-aggregation formation. And then in the thin film, we see clearly these nanofibers formation that didn't exist in the original neat film. And pre-formation is important so that during the drying, then these preformed network can be connected together before the insulators start to get in between them. That's really the key for good charge transport. But still, to our surprise, we were hoping to just maintain the charge transport and not decreasing it. But to our surprise, we found that compared to the neat pure semiconducting film, adding 70% of insulator, we actually saw a boost in the charge carrier mobility. We attribute that to improve the nanoscale order, because the pre-aggregation in solution force the polymer to disentangle and align along the nanofiber. So some of the kinks that may originally exist in the polymer become removed because of this nanostructure formation. And then we can further boost the mobility if we control the coating so that there's some alignment of this nanostructure. And then this mobility can be even several times higher compared to the best possibility for this neat polymer. And this also at the same time allow us to include the stretchability in these materials. So we're essentially adding a new functionality without compromising, but rather enhance the charge transport, which was completely unexpected. And the other finding that's interesting was that the nano confinement actually makes this nanostructure to become softer. The glass transition temperature is much decreased in the nano confined structure, and the crystallinity also decreased because of the nano confinement. And these all both contribute to lower modulus and more ductile material, and make it overall a more mechanically robust material. So with these development, then the charge transport for stretchable polymer semiconductor. Initially, when we first started this work, there were a few reports, including our micro-cracked system and some other systems. Even though nanofiber was used, but nanofiber was combined, mixed with the elastomer, where the elastomer will impede the charge transport. And in our case, with these new design rules, now we're able to take the charge transport to similar level as for those of the best polymer semiconductors. And we're very excited about this approach because it's quite general. As long as we can induce these nanostructure formation, we can not only enhance the charge transport, but add the new functionality. So if we want biodegradability and elastic semiconductor, then the matrix is biodegradable and elastic. And we design it to match the semiconductor. In this case, to make the semiconductor degradable, we replaced the double bond, carbon-carbon double bond with imine. And this was what we reported some time ago by Ting Lei, who now is in Beijing University. And this makes a degradable semiconductor. But putting the two together, we have the new functionality, but still enhance the electronic property. If we want self-healable, again, similar approach, you can already guess. basically we have the semiconductor and the matrix that's self-healable. Even though the semiconductor by itself is not dynamic, it cannot really transport across a gap. But with the matrix, it can carry the nanostructure over this gap. So without any elevated temperature or solvent annealing, the film can be healed. And we also showed this with, for example, silver nanowires or nanoflakes can also have the same mechanism for mechanical healing and electrical healing. For conducting polymer, again, nanostructure is very important. Yi Xuan was a visiting scholar actually from Tianjin University, who was instrumental in this design of this new crosslinker. We previously know that the PEG groups, when added into conducting polymer PSS, can result in improved conductivity because it induce the aggregation of P dot. In some cases, can form nanostructure. But the PEG itself is crystalline, and adding a lot of PEG actually results in a brittle film. And also, even though there's a boost in, to a certain extent to the conductivity. So here, in order to really suppress the crystallization of the PEG, we have to go to the extreme of adding the rotexane to thread over the PEG. And then the side chain have additional PEGs so that then these side chains, we hope they don't crystallize too much, but adding a high density still will lead to crystallization. The other role of the side chain is to carry the crosslinker so that we can pattern the high conductivity P dot using this kind of crosslinker. And this can give even submicron feature size, directly photo patterned, but also high conductivity. So compared to many other approaches, stretchable conducting polymer already exists in literature. But the thing is, to get the stretchability, various different kinds of plasticizers, surfactants, or additives are incorporated. And then with the strain, these polymer typically have much decreased initial conductivity and also with strain. But in our case, for this new conducting polymer with the nanostructure, we start with a very high conductivity already in the a few thousand Siemens per centimeter, which is in similar order of magnitude as ITO. And with the strain still maintains one of the highest conductivity. So this is very important for further development for many devices. So we are now building based on this useful materials. So now with the understanding of materials design, we have a collection of materials ranging from conductors to semiconductors and dielectric layers, substrate, and with added functionality such as stretchability, self-healing, and biodegradability without compromising the electronic property, and in many cases now even with enhanced electronic property. And that's exactly what we want to build the future e-skin. So with the materials, the next challenge is really to put the materials into more kind of larger scale electronics that can allow us to build things that are closer to either circuits or system level. And for that, we have to also develop fabrication method where the subsequent layer, the patterning and the processing will not degrade the previous layer. Our first generation, we were able to achieve 350 transistors per centimeter square. And in that case, we had to rely on the conventional patterning method using photoresist and etching and many steps to pattern one layer. And that makes it more limit the type of materials that can tolerate all these processes. But also the electrode was patterned by basically spray coating and shadow mask and making it difficult to have high resolution. But the most recent generation and the generation forward, now we have developed not only the high electronic performance, but also the patterning chemistry is incorporated directly into the active material. So this simplifies the process and also is important for us to have high yield for each layer fabrication. And then this will ultimately allow us to go to more complex electronic circuits needed. So for the conducting polymer, I already showed a previous example, but in this particular paper, we used a simpler formulation. It's not as conductive as the previous one, but it can, at this earlier version, it was able to get good enough conductivity and high stretchability. And then for the semiconducting layer, we used the diazyrine chemistry for the patterning without degrading the polymer semiconductor. And similarly, with the dielectric material, we used a similar patterning method. So this allowed us to decrease the feature size for both semiconductor and also importantly the electrode material, and going from the first generation of 350 transistors per centimeter square now to 42,000 transistors per centimeter square, but with charge carrier mobility at amorphous silicon level. And I mentioned yield is really important. For example, if we make a simple circuit that has this adder, half adder here, this circuit has only 30 transistors, but think about 30 transistors all working, each has 5 layers to fabricate. And the yield for each layer, if it's 99%, for each layer, then when we make, if we want all the 30 transistors to work, the overall yield after we perform the fabrication would become only 22%. So that means essentially we need 100% yield for all the layers and all the transistors we make in order to really make a working circuit. So that highlights the challenge for basically taking materials to the next step, but it's a necessary step in order for us to really be able to understand what are the next needs. So that's how we essentially get to this newest generation. And next, with these circuits, then they're useful for, of course, the signal processing. And then we also need sensors. I won't go into too much details, but for sensors, basically, there are a number of sensors that we have been working on over the years. And these sensors include force sensors that sense pressure and sense direction of forces, sense the strain and the mapping strain. And this one senses the compliance, basically soft versus hard materials can be sensed. And then finally, temperature sensors using small circuit. So these are important for robotic applications and the many medical applications we're exploring. And then the other applications that are quite unique and really take advantage of these skin-like materials is to map electrical signal from our various organs and from our body. The beating heart, if we want to measure the electrical signal on the beating heart, then we have to accommodate the movement, contraction, and expansion of the heart, and without breaking the electronics. So having the stretchable electronics is especially important. And then measuring inside the brain is also extremely important. People have implanted electrodes inside the brain, and if you make the electrodes small enough, then you can measure electrical signal in one region without damaging the brain. But in other cases where, for example, this brain stem region. This is the region where the spinal cord go into the really converge with the brain. And this is the central highway for all the information to go between the brain to our peripheries of the body, and also for all the sensing information to go back into the brain. But because of the the neck movement, this region experience a lot of mechanical force. So anything rigid can cause the damage to the brain. And this is a region that no electronics have really been able to be placed here to actually map electrical signal in high density. And for the first time that these soft electronic skin electrodes, we were able to make arrays and really map not only which general region correspond to the control of what specific motor function, but determine very detailed resolution to control left side or right side of the whiskers and the muscle movement and so on. So this can provide a lot of new information that previously we did not have before. And then more practical application probably is outside the body. And then here with the high resolution electrode, now we can measure not only just the signal strength from the muscle, but rather these correspond to the mapping of individual muscle bundle that are firing up at different millisecond resolution, and really look at how these signal propagate, and then can allow us to understand the muscle function. So these are some of the directions that we're moving into to see how we can apply these various electronics. And in addition to just being soft and conform to the kind of beating heart or moving body, there is also real performance advantage for these organic electronics, mainly coming from the lower interface impedance between the electrodes and the biological system. So here the impedance basically is the resistance when electrical signal travels between the tissue into the the signal being sensed by our electrode. If there's a high resistance at the interface, then there will be some drop in the signal intensity. Or if we want to stimulate the nerve, then charges need to inject into the nerve. And if the resistance is high, it will require high voltage. But for conducting polymer, because of its high capacitance characteristic due to its high porosity, as well as the ionic conductivity, it has been known that conducting polymer has several orders of magnitude lower impedance at the interface with biological tissue compared to that of metal electrode. So this is really important because that can lead to lower stimulation voltage. This is what we have demonstrated with the conducting hydrogel that we developed, that's tissue level softness. And compared to platinum electrode, which is the red curve here, The y-axis is the amount of leg movement that's induced by electrical stimulation. And with the conducting hydrogel electrode, we can induce leg movement at 10 times lower voltage compared to that of the metal electrode. And then this lower voltage can really reduce the potential damage to the biological tissue. And the other implication is a higher signal to noise ratio. That means when we try to measure these electrical signal to do mapping either on the brain or on the heart, on the muscle, then these electrical signal, we can, with a higher signal to noise ratio, then we can reduce the size of the electrode and have really high resolution mapping, while standard ionic gels requires a large area. And because it only has the capacitive term, it has a very high resistance, but having both the conductivity and the high capacitive term, then we can really start to achieve high resolution mapping. And further advantage is to have a new type of electronics that we call morphing electronics that changes size with or grow with the biological system. For example, if we implant electronics for nerve stimulation into a child, then these nerve stimulators shown here, they even though it's made of plastic and rubber-like plastic, but it's still very rigid, high modulus, and it even has an opening, but still it constrains the growth of the nerve. We did the experiment in the baby rat, which has a small nerve, and after 2 months of growth, the nerve will double in the diameter. So if we design our organic electronics nerve cuff, we can design the material, both the conductive material as well as the substrate, to assert almost no force as the tissue growth over small times, long time scale, but over short time scale, when these when there's movement, the material behave elastically, and then we can conform to the nerve and continue to have a good electrical stimulation or measurement. So you can see the nerve after the implantation, the very clean nerve, and even after 2 months, still very clean, no damage. But with the commercial nerve cuff, it either causes these damage, and also at the same time, because the severe constraint start to fall off even during the middle of the implantation. So this shows a new possibility with such kind of morphing electronics, where we can really think about possibilities for pediatric implants. And finally, a new area that we think is really exciting, that kind of hopefully in the future really leverage biological systems to truly merge electronics with the biological system. That is the genetically targeted chemical assembly, that a new approach to assemble electronic materials in biological system that we have developed. So we're thinking about this mainly because the current paradigm of implanting electronics is to build electronics and insert into the body, and that causes a lot of potential damage, and it's to the body, and it's an invasive process. So we start to dream something really far away, basically thinking about, can we leverage biological system and make electronics basically inside the biological system directly, and that will require specific ways to direct materials and to places we want to, and make conductors and insulators accordingly. And there exists a method that allows genetic targeting that's being widely used currently in neuroscience. That's called optogenetics. Basically, virus is used to deliver genetic material into specific cells, and what virus can attach to certain type of cells, and then that allows the modification of those particular cells, in this case, to become the neurons to become light sensitive. And then originally the brain cannot be stimulated by light, but then now with this modification, specific regions of the brain becomes sensitive to light, and then one can use that to understand how the brain is. The function of the brain and how different kinds of neurons communicate with each other. This was pioneered by my colleague, Karl Desroth. So we got together and we thought that, well, can we leverage this kind of concept to start building functional materials inside the brain? And here we, instead of light-sensitive enzyme, we found that there's a particular oxidative enzyme can also be genetically targeted onto the neuron cells. And this enzyme can, together with low concentration of H2O2, can induce the aniline to polymerize only at the region where it's modified with the enzyme. And then in the control cell, without this enzyme, there's no black colored polyaniline forming. But with all the required reagent, then we can see this black coating. That's basically the conducting polymer coating. And we can coat that onto neurons and actually measure a true electrical conductivity. We put electrodes on them and show there we can measure conductivity. And this can be done in the brain slice and in live organism. This is a C. elegans. It's very small, but contains only a few hundred neurons. So very simple, and it's a model system for neuroscience study. And here we can target the conducting polymer either on the inhibitory neurons or on the excitatory neurons. And they control the body movement. One is restrict the body movement, when one allows body movement. And then we can see the difference in the movement that shows that indeed culturing these polymers onto the neurons can lead to selective change in behavior. So now to summarize, I give you some highlight of recent development of skin-like electronics, mainly from materials development, which is the foundation, serves as the foundation to a number of different devices. That's the core for building any integrated system. In terms of transistor arrays, so we are going to even higher density and higher charge carrier mobility. We recently reported a fast diode, which is needed for these wireless tags. Next, I hope come out later this month or early next month is a new type of high luminescent polymer, stretchable polymer LED. And now it's going to allow us to think about making displays. And then there's a battery and various sensors, all are key component. And now we can see that one by one, they're all possible to be realized with electronic properties that's comparable to the best flexible devices. So I think they can potentially open up new possibilities. So finally, I'd like to thank my research group. Actually, much have changed. This was our first get together since the pandemic, and now many people have moved on, and the new people have come in, and many collaborators in Stanford and in other universities and all over the world, and funding agencies and many seed grants in Stanford that allowed us to explore these new areas. So thanks again for the invitation, and I'll be happy to answer any questions. Thank you.
好，谢谢鲍老师的精彩报告。那鲍老师，我们讨论的时候用中文，你看可以吗
？OK， 可以。
好，谢谢鲍老师的报告啊。鲍老师您先。
谢谢芷兰，这个报告真的是非常精彩的，大量的那个引领性的工作、原创性的工作，确实学习了。芷兰，我请教2个小问题。那个第一个就是你刚才我还是确实给证明到了这个刚开始从你的1代那个集成那个晶体管是350个晶体管每平方厘米，到现在第2代是42000个了。我估计你刚才讲的你的第3代要到10万个。对，所以我觉得这个是这个领域里面的一个我觉得一大波一个跨越性的一大波。我想问的是这个器件的均一性怎么样？就是说现在这个所有器件的那个uniformity 啊，那个性能均一性怎么样？
均一性的话，那个应该是 within 它的那个像我看前面的这个in terms of mobility， 我们这边有一个 chart， 这边这个是均匀性。关于 mobility 这边有100个 transistor，and then 这个 mobility quite uniform. And then 这个其实 with high density 的话，其实那个100个 transistor 它占的 area 并不是说很大。如果是 low density， 反而有时候均匀性反而会比较 difficult， 因为我们 spin coating 啊或者什么这些还是有一些限制的。但是I don't have the exact number. I need to see what's the exact number. But my recollection is 就是说是 within 20% 肯定是的，那个 current output 什么这些，threshold voltage 好像就是说它的那个均匀性会差一些但是像 current output 好多这些还是quite uniform。
对，这几个参数 uniform 就已经可以推动应用了，这个确实是一个巨大的进展，非常有引领性。
这个是而且就是说这个42,000的话，这边其实只是 transistor， 还没有 interconnect。你可以看到只是 transistor， 所以呢，那个下一代的呢，我是跟学生讲说要放 interconnect 才算，因为 interconnect 那个更加难做，要 integrate 起来的话，所以那个100,000的话是包括 interconnect 的。如果不包括 interconnect， 可以是200,000。
哇，那实际上就是互联的连线里面都包括进去了。
对，就是这个 stretchable interconnect 也是一个 key 对，所以那个是这个做这个 student 很 remarkable， 是彭烈苗的老师的学生，在我这里他给到了从东来做的对，
厉害，做得非常好。第二个问题，那个芷兰，这个因为你做那个现在叫电子皮肤引发的这种 研究啊，实际上你现在也跟那个脑科学啊，跟那个神经科学啊，都已经关联的很紧密了，而且也是很前沿的了。我想问一个比较通用，就是说，你觉得这个最有可能就是说这个电子皮肤啊这个领域最有可能在哪一块率先能够应用上？
其实我觉得这个就是穿戴在身上的，其实就是说脑科学或者什么这些的话，我觉得有很多 opportunity，我们等于是 provide 一个 tool 去 understand 有很多新的这个 science 可以去 understand。比如说我们现在还有 incorporate 像 neurotransmitter 啊这些 chemical sensor 也都可以 incorporate， 然后不光是在脑子里面可以 implant， 还可以在那个肚肠里面 implant， 像肚肠这些的话都需要很软的，那这样子这些的话以前都 did not exist， 所以那个呢是 more for understanding。这个跟生物啊、脑科学啊什么这些结合起来，那个是 very longer term， 我不知道什么时候真正的 application 会 really start。It's more for fundamental science understanding。然后我觉得 more practical 的话是 outside the body。outside the body 的话，其实就是说像这些可能这个 image 我没有太多去讲。这个是我觉得something that's quite practical 这个我们叫做 body net， 这个是 first generation。然后这个 first generation 的话，最主要的话是说这个是一个 wireless 的 tag， 它是 passive 的，然后那个读它的信号和它的 powering 都是从 external 的这个来。这 external 的话，如果不把它放在身上的话，放在衣服里面，只要在近处附近的话，它等于就是 RFID 这样子。它在附近的话，它就可以去 power 这个 tag， 然后可以 sense information。那在身上的这部分呢，就不需要说就是很 bulky， 然后也不需要电池，也不需要去 restrict 我们的 body。但是呢，这个 tag 我们以前的 tag 的话 too simple。Too simple 的话，因为它没有我们没有 circuit 的 capability， 所以只能放 sensor， 而且只能放 capacitor sensor。但是现在我们有了这个 diode 了的话，这个 diode 很重要，因为 diode 的话就可以把 AC information convert 成 DC， 所以我们的 new generation of diode 有了之后，我们现在可以放 display， 可以放小 circuit 需要 DC voltage。去 power 的 circuit， 还有 resistive sensor 都可以放。那这个 tag 就可以大大的 become much more complicated。And then 我觉得这样子的 sticker like tag can have a lot of potential applications for 那个 health monitoring disposable 这样子。所以这个是我觉得就是说 maybe more near-term 的 application。 Then of course 如果这个 battery 可以解决的话，那这个 battery 就可以作为是 substrate， 然后把 sensor 什么都 integrate 在上面。那这样子的话，这个也是 new form of这个 wearable for health monitoring， 我觉得那个也是有很大的 possibility， 很多潜力。
对，这个实际上这个柔性的那个锂电池，现在他们也做得很好，所以两个一集成的话，实际上做个健康监测就完全可以了，对吧？
对，但是现在的这些就是 flexible 的 battery 其实并不怎么 flexible。它是对，你不能 bend 太厉害 ，bend 了一下它就那个坏掉了对，其实 there's a huge need for 这种就是 energy storage device that's high energy density， 然后又可以储存那个又有这样子的 form factor， 又 stable 的这样子的这个还是不容易做到有很多 super capacitor， 但 super capacitor 储电量太少了。
对，那个，所以的话，实际上还是要把那个柔性的锂电方面如果突破的话，
对，这边
也有保障的，
很多 opportunity 对。
好，谢谢子兰，谢谢你学习的非常感谢，非常感谢。立翔，
请问其他老师和同学还有什么问题吗？
鲍老师好。
哎，
好，宇轩，
轩
你好。
鲍老师好，好久没见了。
那
李老师，我提个问题可以吗？
可以，宇轩你。
好，鲍老师。每次听您的报告都是一个非常有目标的一个有规划的系统性的研究，都能学习到很多您的这个思路啊，非常感谢您的报告。我这儿呢，因为您也知道我是一直在做材料的这个研究，包括它的新的一些超分子结构的一些设计，所以在做这个有机材料的时候呢，就总有这个其他同行啊或者其他材料科学的人去问。就是说有机材料，尤其是有机电子材料，它毕竟它的电学特性目前来看呢，还是有一个 limit。那么您觉得除了这个力学上有机材料确实有很好的一个前景之外呢，那在有机电子材料方面，除了力学特性，有机材料还有哪些potential 的一些性能是无机材料所不能媲美的？您觉得适合就是更多的去深入研讨的地方啊？这个向您请教。
我觉得就是说，首先我就不同意说general 的assumption。有机材料就比无机材料差 ，in terms of electronic property。其实有机材料已经可以至少跟 amorphous silicon 一样的，而且有 quite a lot of candidates can be as good as polysilicon。The reason 它这些还没有 really enter the mainstream is because 如果 it's simply trying to replace existing 的这个 application plug-in 换成有机，那这个manufacturing facility 都已经for polysilicon amorphous silicon 都已经在那边了，那要再去 invest in figuring out all the manufacturing facility and then simply to replace the material without much advantage 的话，那这样子就没有一个 driver。所以的话是before 没有一个说 application 真正的 take advantage of 有机材料的所有的 combined 这样子的 property with good electronic property, but there are additional attributes 可能还在下面可以也是跟环境有关的 right sustainability 或者 all of these 就是说那这个什么样的 application 是最适合的？那现在的话，而且 previously 像 monitoring device、wearable device 也没有 so much being accepted， 也是 partly because 这个 AI 的 development 使得本来那些 sensor 太多 variation 了，无法真正得到好的 determination for disease diagnosis. But then for health monitoring combining with the AI 的话，那这样子可以得到 information 是 meaningful 的。那就是说，我觉得是好多 aspects now start to emerge, and then 当然是这个要 identify 真正的一个最重要的 product 的话，我是觉得是这样子 monitoring device。当然 of course 是 which monitoring device， 那这个是最 suitable 的那这个是potentially 我是觉得 electrophysiology 的 measurement像 measure 一些那些electrical signal from the body and then where circuit actually is needed， 因为这些 sensing information 都是太 weak 了 signal， 所以你需要 circuit 就在这个 sensor 的旁边，而不是说像现在的 sensor 都是你有个 silicon chip， 然后 sensor 只有一个 sensor 没关系，它立刻就接到这个amplifier 上去了。但是你如果要把 sensor 全都 spread over large area， 那你的 amplifier A to D 全都要 next to the sensor， 那这个的话就 create new functionality new possibilities， 就是现在的这个那个无机材料所做的这样子的 wearable 是做不到的。
好，以前还有问题吗？
我没有问题了，谢谢鲍老师。
鲍老师，我们那个直播平台有听众提问，就他问一下这个目前N 型半导体的进展如何？ 您去介绍一下，谢谢鲍老师。
N 型的半导体的话，那个就是在整个这个有机电子这方面的话，那个 non-stretchable 的有很多good 材料 developed 的depending on 什么样的 circuit 如果是以后就是 more higher level of integration 的话，那 N-type 会很重要，因为否则如果用 P-type 的话大部分的小的 basic element 或者 for most circuit 我们可能需要至少 double the number of transistors needed compared to 如果是 CMOS 的 circuit 而且 power consumption 也会比较多但是在那个现在的情况下的话，就是说还是那个 stability 还是有一些，就是 air stability 还是有一些问题特别是在 stretchable 的里面的 report 的 so far 在 flexible 里面的有很多新的比较好的材料，像Toby Mark Group 然后那个培坚 Group 和还有Wanping Group 什么都有 report 一些比较好的 flexible 的using our general approach 我觉得可以 turn them into stretchable 当然还 require some detailed investigation 但是我觉得做 stretchable 应该不难
好，谢谢鲍老师。其实现在这个 N 型材料可能即使是这种非可拉伸的材料，这个稳定性可能确实还是个问题。因为对于水氧比较敏感。然后最近其实我们也一直在做这个方向，也希望提供。目前好像也有一些进展，希望有机会向鲍老师再汇报一下。
好的。
然后其他老师，刚才是刘老师刘祖刚老师可能想提问。刘老师，那您打开摄像头。
对，我跟几个问题跟鲍老师请教一下。鲍老师你好，是一个非常好的报告，你们的工作是 very beautiful， 也是学习了，一直听说鲍老师工作做得特别好。然后我以前也是做一些打印印刷这个有机。特别是发光方面的工作，我知道您一直在做这个electronic skin 这方面的，所以呢，我刚刚见证报告，我觉得是还是非常 exciting， 就是说，特别是你的那个这个 density 这个 area 的 density 提高得很高，所以呢，我可能前面有一点点我有点没有太赶上。所以我想跟您请教一下，就是说，你们是好像说是用这个 lithography 的方法来做的
对，
就是说，如果就是说你要是多层的话，这个 lithography 是不是怎么实现的？另外一个就是说，您刚才提到说，要提到更到里面的有那个 interconnection， 这个 interconnection 是不是也是同样的方法吗
？OK， 这个就是这个做多层的话，其实基本上我们的这个 lithography first generation 是用就是 traditional photoresist， 然后呢 photoresist 它是作为一个etch 的 protection 的这个 layer， 或者然后我们还要 combine with the metal， 还有其他的 protecting layer， 这样子我们的 semiconductor 才不会 damage。但是我们的那个 more recent 的呢是用这个我们的 semiconductor 或者 conductor 或 dielectric layer， 它都是就是先 coat 一层，然后呢用就像做 photoresist 一样，它这个 UV expose 了之后，它是 crosslink 那个 active material， 那部分呢就变成是不能溶解的，就像 negative photoresist 一样，但是这是 active material， 那我们洗掉了之后，它就得到 pattern 了。然后这样子它 crosslink 了之后，我们在 coat 下一层的时候就不会把它 dissolve 了。这样子就一层一层可以叠加上去。
这是 UV current 这么一个过程是吧？
就是
那个 UV current 这个
对对对就是用 UV curing 一样的，它是 cross link， 这个留下的这层就是不能溶解掉的。
OK，
对，
谢谢。包老师，另外一个问题啊，因为我知道您这个在电子皮肤方面做的工作的确是很好的。就是一般的来说，目前来看，我们关于就是说我们来模拟皮肤的一些其他功能的探测或者功能化已经基本上实现了。现在就是说一直大家都在提说关于这个痛感的这个检测方式您看这方面有没有新的进展，或者有一些什么展望方？
我不知道有没有什么太多新的进展。那个几年前跟Stanford 这边的关于治疗疼痛，然后还有麻醉的这些医生有谈过，他们是说就是说这个痛到底怎么去用一个定量的方式去测量，首先是比较的还不是很清楚。那个因为每个人讲那个痛的话，人和人之间的他的这个准则是不一样的。那个是用什么样的方式去测量它？到底是用心跳的速度、血压，还有皮肤的导电性，还是温度？或者甚至一些 chemical species， 像 cortisol 或者其他的 chemical 那个分泌出来的 chemical 这些还不太清楚。所以的话，first 就是 to quantify 什么叫 pain，这是一个 first thing， 然后有了这个 quantification， 然后我们才可以说有治疗方法到底是有没有用处，否则都是 qualitative comparison。所以that's all I know。我不知道是不是有什么那个新的进展 in terms of 那个能够 quantify 这个 pain， 好像这个还是 up to debate。OK，
谢谢。因为为什么我对这个感兴趣呢？因为我以前接触过一些医生，他是做这个叫 pain management。这个 pain management 就是说我告诉你，因为你这个那个 pain 到底是什么地方？到底是就是你的感觉是不是啊？你们刚才您说的这个度是怎么确定？因为是根据你自己的感觉是吧？才能有的人痛的比较感觉到厉害，有的人感觉到弱，或者呢你通过那个 management 就可以使你这个痛感减轻。所以就是说这个可能的确是有一点点不太好这个定标是吧？
对。
好的，谢谢你，包老师。
好的。
包老师，我也请教您2个问题。第一个问题就是，我看您有一个表，就是目前比如对比有机材料跟其他的一些工程材料这个迁移率的这张表，然后我看您那里边提到了这种通过这种应变工程或应力工程，可以让有机小分子这个迁移率可以，我看您是画了一个有可能达到上千，这是理论预测的结果是吗？
没有上千，这个只是 pink 的，全在 pink 这边。可能这个 misleading， 这个箭头指的才是可以达到的。对，没有上千。
好的，
都在集中在差不多这个 region。
对，因为我看过您的 Nature 那篇工作，就是非常有开创性。然后比如说因为对于这种因为我们在很多材料里边，如果存在应力或者应变的时候，其实它的这种力学稳定性可能会存在一个问题。这样有没有可能，比如说你通过这种应变工程它虽然提升了它的迁移率，但是是不是因为它体系处于一个相对不稳定的一个状态，反倒对它这个稳定性，比如说保存稳定性会有一些影响吗？
这些的话就是像这个它是basically 这些是 crystalline organic， 就是我们以前 reported 的那个像 tips pentacene， 它的那个 lattice 会有那个 distortion due to 它的 trapping of the metastable state， 所以那个确实不是它的 most stable state。但是因为这些 material 的话，它是 collectively 都已经就是 organized into that metastable state， 所以要把它全go to 那个 equilibrium state 的话，需要一个很高的温度才能 cooperatively 让它 turn back to the 那个 equilibrium state。所以的话，那个 metastable state 还是至少 for TIPS pentacene 那类的 molecule 还是 quite stable， 可以到100度以上还是 maintain。
对，因为100度可能对于有机材料就是它的应用就已经足够了。然后还有一页就是我看您现在目前的，比如说未来的一个发展方向，就是这种可拉伸的 OLED OPV， 我期待也见到您这个最新结果能报道出来。但是挺好奇的，可是这种可拉伸的 OLED OPV， 它的拉伸过程中，它的这些基本的这种光电性能是怎么样一个变化呢？比如说你可以想象一下，比如说这个 OLED 它拉伸过程中它是整体的亮度，
那个亮度增加一些，最主要是那个 thickness 降低了。但是也是 depends on 那个 device engineering， right？ 因为这个对于这个 optical device 来说的话，它还有一个 optical cavity 的这个影响。那我们现在都没有去管这些，我们而且这个 thickness 的那个relative thickness for 不同的 layer 的话，像在 Polymer LED 会 control where the charge recombination happens， 所以的话，那这个layer 的 thickness 如果 distort 的太多的话，也会影响它。如果 recombination 就不那个不在 no longer in the center of the emitting layer， 也会有问题呀。我们现在没有仔细的去 study， 我们现在是发现 a way to make these kinds of light emitting polymer to basically reduce the carrier traps when introduce 这个 stretchability but then reduce electron 和 hole trap， 所以这样子的话，我们可以加一个另外的 material but still have actually increase the luminescence because we reduce the traps and then can achieve 这个 stretchability and then using the 你saw这个 P dot 这样子的 polymer， 我们有 stretchable P dot 这样 incorporate 进去的话，就可以做stretchable 的 PLED。
这个应该是非常非常新奇、非常有吸引力的一个结果。期待您的尽快发表。然后看看其他老师和同学还有没有其他的问题。
鲍老师，我可以问一个问题吗？
炳浩。
你好，我是王炳浩，那个Topic Max 组的之前的博士后。我想问一个关于那个晶体管阵列的一个问题，因为我也是做那个有机晶体管。我发现我们做的这些晶体管大多数都用 spin coating 的方法来形成这种就是垂直相分离结构，从而可以做一些就是可拉伸的这个晶体管阵列。但是对于商业应用的话，可能就是说 spin coating 可能不是一个最佳的一个 solution。如果用其他的 coating 的方法，能不能同样的形成这种垂直相分离的结构，从而可以形成这种大的这种大面积的阵列？这是我的一个问题。
从理论上说都是可以的，就是这个 matter of detail， right？ 这个to figure it out 是什么样的 exact condition。比如说像这个 case 的话，我们的高的 mobility 其实是用 solution sharing 那个 method，而且 solution sharing 的话 ，without 这个 pillar。就是 flat blade 的话，也是有一些 improvement in mobility 的。这个就是 blend system， 我们在 solution share 的。所以这个是 当然 vertical phase separation 跟那个 interface 很重要，像我们要得到这个我们所要的这样子的vertical phase separation 的话，要有那个high aggregation 在 either top 或者 bottom surface 的话，这个 dielectric surface 我们发现必须是像那种 OTS 或者 some kind of hydrophobic surface for 这个 combination in order to get the right phase separation 所以 interface 也是很重要。
对，我也做的 DPP、DTT， 然后和 SUAT 的一个混合体系，发现，如果不用 OTS 处理的话，这个性能非常的差。
Yeah， 它的那个 phase separation 完全就变了。
对，好，谢谢包老师。
尹浩在晶体管方面也做了非常优秀的工作，还有柔性电子，他是池老师的学生，在那Optogenetics 组做过博后，还去扫描组织。现在在东南大学。
OK。
包老师，那个唐伟老师，上海交大的唐伟老师还有一个问题请教您，因为他可能是这个语音不方便，他问一下，就是这个，比如现在目前柔性电子和可拉伸电子，他觉得哪个可能更快的是走向实用化？这可能是比较一个宽泛的问题。
那当然，那个就是说产品的话，先出来产品的话，那这个柔性电子已经发展了很久了，所以的话，那个要就是说做产品，那当然这个已经从实验室早都已经 translate 到 industry 了，像 Polymer 这些company 的话，它 already have process to make 这些circuits over Gen 3 type of Gen 3 even 到 Gen 5这样子的这样子的 substrate 的 size， 所以的话那个要是 product 的话，我觉得肯定还是柔性的会先有 product 的。那 stretchable 的话是现在才开始有实验室的 demonstration 说可以达到那个柔性可以达到的这样子，所以的话，那下面再从实验室再去，因为这些材料的话，它的那个性能还有 processing 上面还是跟柔性的有些差别，但是很多是相近的最大的可能我觉得那个不同的话，就是说 thermal expansion for 这些 stretchable 的这些 material， 它 intrinsically 它的那个 thermal expansion 就会比较大，所以做那些那个要去实际应用的那些生产的话，那这些 thermal expansion 你不同的 layer 你如果加热了的话，它到时候就不 match 了，有很多这样子的实际的那个问题还是需要解决的。
好，谢谢包老师，也在唐伟，谢谢包老师。